Hey gang, welcome back for another video here on jOeCHEM. My fellow jOeChemists, if you're watching this video, that means you've fought, you've persevered, and you've clawed your way through alpha carbon chemistry. So this is kind of like our little victory lap, if you want to call it that. In this video, I want to do 3 synthesis problems. One, I will say, is a little on the easier side. The second one, I'll say is a little bit more advanced. And the third one, it's a little sneaky. But the best part is when you do synthesis, you don't realize it, but even if you don't get something on the first try, you're exercising your brain. The organic juices are flowing and you don't even realize it, but sometimes you're putting connections together even when you're trying something that isn't maybe the correct pathway for a particular synthesis problem. You're forming connections in your brain under crunch time. So doing synthesis and not succeeding on the first time is still progress. And in this video, we're going to, deconstruct each of these problems, regardless of the difficulty level. And I think you'll see how everything we are learning with alpha carbon chemistry can involve stuff that we've done with carbonyls, and scarily enough, even stuff from Ochem I. But no fear, right? We never get worried with synthesis, right? We freak out for 1 second, take a deep breath, and then we attack methodically and with a level head. So, I'm gonna pause the video, I'm gonna throw up a problem, and we'll get this party started. Okay, gang, so let's take our crack at our first problem. So, I know some teachers, and this is the correct way, they will draw something and then they'll use, the retrosynthetic arrow terminology and whatnot. I've always just been a fan of getting a big open space, whether it be on loose leaf, horizontally, or whatever, big chalkboard, big whiteboard, putting what I'm trying to get to over here and working back this way because we always work backwards. Okay, so we have 4 carbons or less to work with, and this looks a little a little wild over there. But I hope you realize, because in actuality, it's not that scary. So I know our very first step is count carbons, right? And we can still do that, but don't get tripped up on accident. And I hope you're even realizing that we have these 2 acetal groups right here. Right? And they have carbons within them, and when we do our carbon counting, we're not gonna, include them. So let me just go ahead, even though I just drew those pretty pink dotted lines, I'm gonna erase them. We know those acetals are not supposed to be in our carbon count, so we're just gonna deal with a 1, 2, 3, 4, 5, 6, 7, 8 carbon target, which is amazing because we're allowed to work with 4 carbons or less, so we know we will eventually get 2 4-carbon pieces. Life is good, easy breezy, good time to be alive. Okay, and I'm even gonna erase these numbers because we know that there's 8 now, so no reason to keep them along for the ride. Okay, so remember, we work backwards, and I think by now, if you've been watching my videos, I like to do it down and kind of up and use all the space I have given to me. So, I hope you're thinking the easiest thing is, these are acetals, right? I hope you've realized in synthesis problems, sometimes the big connecting steps, while they are like the toughest thing to get to, someone can make a problem a little bit more difficult by dressing a molecule up after you do a connection. So I think this last synthetic step, I think my molecule looked like this. I think I just had 2 ketones, and the reagents that got me there, right, when I have 2 carbonyls, I know if I threw in H3O plus some acid, could be whatever, but we can just use H3O plus, and not the necessary step, but minus H2O, we know that happens when you do acetal formation with a carbonyl. This is what got me from here to here. Okay, so nicely enough, let me just make sure I didn't lose any carbons. 1, 2, 3, 4, 5, 6, 7, 8, bingo, cool. This looks a little bit more manageable, right? So yes, this was like a little bit of a carbonyl chemistry step, and you're maybe watching this video thinking, okay, Joe, but where's the alpha carbon stuff? That's why I'm here. Well, lucky for you, we're just about to get there. So whenever I do synthesis problems dealing with alpha carbons and their chemistry, it's really easy to forget everything you've learned because you know you have so much stuff going on upstairs and you're just wondering what reaction you're using. Never forget the things we've learned. With an aldol reaction, we get a molecular relationship that's a 1,3 hydroxycarbonyl. With an aldol condensation, remember, we get an enone. With a Michael addition, we get a 1,5 dicarbonyl. And unfortunately in this video, I'll just be straight up with all of you. I didn't do a Robinson, but remember, you can always go back to the Robinson videos I made, relive the good memories on those videos. So, it's really important to remember these relationships because when you look at a product, you will know what reaction you used based on identifying these relationships. And I hope that once I wrote that on the board, or maybe even before I did, because you are all very smart, they looked at the molecule and said, okay, well I see 2 carbonyls, maybe smelling like a Michael addition. Let me do some numbering. 1, 2, 3, 4, 5. Bingo, bango, bongo. The connecting step here was definitely a Michael addition. And of course, knowing the relationship's not enough, you need to remember how to do a Michael addition, right? And a Michael addition is when you have an enolate and the enolate attacks an enone. And I'm going to take a quick second to revise something I said in my Michael addition videos. A Michael addition is only when an enolate attacks an enone. When a cuprate does it or something else, it's just called a 1,4 addition. A Michael addition is a specific type of 1,4 addition. So just covering my tracks from my previous video. Okay, anyways, big sidetrack from saying we had 2 acetals at the end. We knew if we step that back and we, use water or subtract water and use some acid, we get this lovely dicarbonyl, which was the result of a Michael addition. So if we step this back, right, I know I need an enolate and an enone. Luckily, we can make a cut. Now let's make a cut here that is beneficial to us. Let's make a cut that, if possible, will give us 2 different 4-carbon pieces, because then that makes the problem very simple. Well, luckily, I think I see a 1, 2, 3, 4, and a 1, 2, 3, 4. If I make this cut right here between 2 and 3, 1, 2, 3, 4, 1, 2, 3, 4. So I need to kind of do enone and enolate. So I'm just going to randomly say this bottom piece right here, I'm just going to say that's the enone. And remember, Michael additions are a 1,4 addition. Actually, I always number this. It's not technically wrong, but it is wrong. 1, 2, 3, 4, right? We don't do a 1,2 addition, we do a 1,4 addition. We attack here where there's a partial positive charge. Cool. So there's my enone. Now I need to make sure I draw the correct enolate. So remember, look at where you connected from. I know I have 4 carbons like this, and I know my carbonyl is on this 3rd carbon in, and I'm going to draw him I'm going to draw this enolate like this. So remember, it's on the interior carbon. That's what my enolate looked like. So this, I would say, is the biggest step in this problem. If you can recognize, okay, step this back from the acetals to the carbonyls, recognize the 1,5 dicarbonyl relationship, then step it back once more, knowing how to make your cut to be very convenient for yourself to give you an enolate and an enone. And you could definitely have this be, well actually, I'm going to take that back. This has to be the enolate and this has to be the enone because given the connection points, right, the other pair would be this. Well actually, right, we would need this carbon to get attacked and this carbon be the attacker, and that just does not work out. You can go ahead and try and draw that on your own. It's just, this is the alpha carbon, and we connect them from here, we're connecting to the 4 carbon there, so this has to be the enone, that is the enolate. Okay, so the best part is, because of the ambiguous problem statement, that we can use 4 carbons or less, bam, this is starting material. Easy, done. We just need to kind of make this, I think you could maybe get away with it, but it's so easy to then take this back just one step further. we need to get back to this, right? This is starting material. 4 carbons, neutral compound. You can definitely buy this off the shelf from a chemical supplier. So now we need to lean on a little bit more of our alpha carbon chemistry knowledge, because this is an asymmetric ketone, right? I could make the enolate, I could easily make, hold on, let me do it this way. I could very easily make this enolate, right? So remember that your difference between making a kinetic enolate and a thermodynamic enolate. This, the one with the enolate we do have, is the thermodynamic enolate, because of the fact that the double bond is more substituted, because this would be the lesser substituted double bond. So remember, for a thermodynamic enolate, you need a small base and warmer temperatures. So what we've used, like I said, use whatever conditions your teachers use. So that's sodium hydroxide, 0 degrees Celsius, solvent THF, bam. So really, this is only 3 steps. 1, 2, 3. Super short, but it did involve a lot of thinking, right? I don't think this is the most earth-shattering synthesis problem, but if you don't know how to recognize a Michael addition, you might get one step and then be SOL, right? Down the river, no paddles, staring at a blank paper, getting ready to cry, boogers everywhere. It's not pretty, okay? However, we know our relationships. We know what produces those relationships, and we got the problem right. Okay, let me clean this up, and we'll move on to a slightly more difficult problem, but it doesn't matter, because we're gonna get it right. Okay, gang, problem number 2. So if you can see here, we got our final product right here, and over here, the rules are 4 carbons or less, and we get the glorious luxury of also using benzene, which is good because we clearly see a benzene ring in the final product. So, what to do, what to do. So if we look here, I hope, I pray, and I did draw it a little bit skeevy, a little sneaky, but do we see, the first thing maybe that jumps out at us is, do we see anything right off the bat that we see above? And I know we're not counting carbons, but sometimes you just can't help but peek, right? So I hope you're seeing carbonyl. Okay, I don't see another carbonyl many distances away, certainly not a 1,5-dicarbonyl, so no evidence of a Michael addition. Don't really see an enone, right? I don't see this structure at all. None of that. But, doesn't quite look so normal. However, if I count 1, 2, and 3, would you look at that? Carbonyl on 1, carbon on 2, and on 3 I have an alcohol. By good golly gosh, that's a 1,3-hydroxycarbonyl. So, we know that our big step in this reaction is an aldol reaction, which is great because they're easy. Those are cake, right? So, what might be a little less cake is how many carbons we're working with. So we know the benzene ring is going to be 1 unit, right? That's one right here. Then off of it, right, let's count our carbons. 1, 2, 3, 4, 5, 6, 7. Unfortunately, that means we're definitely going to need 1 benzene ring, another piece, a 1 4-carbon piece, and then another 1 3-carbon piece for a grand total of 3 pieces. But the best part is we know exactly how we're going to stitch the big parts together, and then once we break this down, we're going to make 2 mini synthesis problems, and we'll have this problem solved in no time. So, the first step is the aldol reaction itself. So those happen in base. So you don't really need like very specific conditions for this. If you just put hydroxide and water, it's good enough. So we need to remember what makes an aldol reaction is an enolate plus a carbonyl in basic conditions. In base. Sorry, I had a momentary brain fart. Okay, enolate plus carbonyl. So it's very easy to identify which one was our enolate. It contains the carbonyl. So we need to have an alpha carbon, and this carbon I'm asterisking is what was the carbonyl that got attacked. And this carbon that I'm dotting was the alpha carbon in the enolate. So it's very easy to see, our cut is right here. So if I go down here, that was my enolate, and over here will be my, so 1, 2, 3, 4, 5. So it's a 5-carbon chain. I know this is a little funky. 5 carbons, darken this a little bit. And it's on carbon 2 that we had the carbonyl. I know it's drawn a little mangled, but that's how we break it down. Okay, so our problem just got significantly simpler. So I'm gonna work with this benzene piece because I think you'll see it's very easy to stitch together. I'm gonna go ahead and kind of draw my arrow down like this. So right now we need to do the enolate formation, right? I definitely had, I'm gonna stick with drawing these in black. Sorry, I keep jumping with colors. It's just whatever marker ends up in my hand. I definitely had this, right? And there's only one way I can make my enolate, right? Because of the fact that my only alpha carbon that has hydrogens is to the right. So I'm just gonna pick a very simple base. Even if you just use LDA or some sodium hydroxide, that is where you'll do the alpha deprotonation. So that's good. Now we need to take this over here. And actually, I'm gonna take back what I said up here. I did some bad math. We're gonna need some more pieces. So what we can do here, and this is gonna pull back a little bit on your organic knowledge, but it's still Ochem II. But if we know we need to use just a benzene ring, right? That's one of our starting materials. And we need to stick this 2-carbon piece on right here. Well, what's super easy for us to do to stick pieces onto benzene rings is if I just grab a 2-carbon acyl chloride, right, from our aromatic or our electrophilic aromatic substitution days, and I throw a little AlCl3 on it, that will take this carbon and stick it right on the benzene ring. That's how we get to the end part of our enolate piece of this synthesis problem. Okay, so 50% done, 50% more to go. So we need to do a little work here. The best part is, right, we have 5 carbons. So we need to just somehow split this sucker up and we'll be on our way. But the best part is this is just an Ochem I problem now, right? What we can do is we can step this back one. We get carbonyls by oxidizing alcohols, right? So use your favorite oxidizing reagents. You could use PCC, or you could use the H2SO4, sodium dichromate, the Jones oxidation, or if you use green chemistry, go for that. Just make sure you put something in the mix that takes this alcohol and oxidizes it to a ketone. I'm gonna make this a little bit lower, PCC, cool. So now, this is something that we can actually cut. And if I cut it right here, I can draw 2 individual pieces of a Grignard reaction. So if I were to do, there's my carbonyl, 2-carbon piece right here, and then I need to draw a 3-carbon Grignard. Okay, so this is done. It's less than 4 carbons. This is almost, I mean, it technically is done, but we're gonna be good senior citizens and we'll just step it back once further. We'll throw in some elemental magnesium and we got this from propyl bromide. So more steps to this problem, but nothing different from the new material we've learned, right? All of our alpha carbon chemistry was super easy to do. The annoying part was actually kind of reaching back for the older stuff, the Ochem I knowledge and the electrophilic aromatic substitution knowledge, right? We saw the 1,3-hydroxycarbonyl right off the bat. We knew we had to step it back. We knew what our enolate was. We knew what our carbonyl was. We easily knew where the carbonyl we got the enolate from. What was a little bit tricky was remembering it's super easy to stick, a carbon-containing piece onto a benzene ring, especially if there's a carbonyl in that benzoic position, the position right off the benzene ring, by making it an acid chloride and throwing in our AlCl3 catalyst with benzene, well in this case benzene. Then we had to yank all the way back into our brains for some Ochem I knowledge by taking this 5 carbon piece and knowing we had to get pieces below 4 and going this route. Okay gang, we're gonna do it one more time. I'm gonna erase the board, and then one more problem that is sneaky almost in the fact that I think it's easier than it might appear, but you'll see what I'm talking about. Okay gang, 2 down, 1 more to go, and then you have definitely tackled what I think to be 3 pretty comprehensive, challenging, but also very thorough synthesis problems. Okay, flipping the script a little bit on this one. We have our final product over here. However, no more degrees of freedom. I'm specifically saying you have benzene to work with and this to work with. As many of each as you want, but that's what you're doing. None of this, 4 carbons or less kind of nonsense. So, what we should do at first, what we're gonna do is count our carbons and also see if we see any relationships that kind of jump out to us. So obviously we see the benzene ring, obviously. Off the ring we have 1, 2, 3, 4, 5, 6. Well, this is a 1, 2, 3 carbon piece. So this is looking pretty good for us to use 1 benzene ring and 2 of this alkyne species, right? Okay. And hopefully, because this is what I would do, obviously I made the problem, but you see 2 carbonyls. The Michael addition note is not that far away. 1, 2, 3, 4, what? That's not a 1,5 dicarbonyl, this is a 1,4 dicarbonyl. So, that's kind of the crux with this problem when I was cooking it up. This is seemingly the product of a Michael addition, however it's not. And this might be that 1 second moment, right, where you think, how am I gonna solve this? But no reason to fear, because we're smart, resourceful, and gonna get this right. So, if we step this back, or if we draw an arrow as if we are gonna step this back, we need to really kind of think of what we're doing, or possible things we could do. So, if we take another look at this, hopefully this may calm you down. If you're thinking, what is it? 1, 2, 3, 1, 2, 3. I think it's not too much of a stretch to say that you can look at what's off of the benzene ring and think to yourself, I naturally see 3 carbons going this way, and maybe these 3 carbons attach to the 3 carbons I see down here. So maybe you're thinking to yourself, maybe you don't know how it happens, but there's a break right there. We're not quite seeing how it happened or what reaction did it, but there's a connection there, and it happened like through a pathway that wasn't one of those 3 things. And I'm gonna write this up on the board, and hopefully maybe something clicks. Never ever forget that enolates can always just do regular old SN2. And hopefully, maybe, obviously you can see that there was some action here at the alpha carbon next to this carbonyl. And we see 3 carbons in a row. And there's an attachment at the end of this 3 carbon chain. We see a good leaving group at the end of this 3 carbon chain. So I'm gonna spoil it, but the crux of this problem is that we didn't do a fancy Michael addition. We didn't do a spectacular aldol reaction or condensation. We just did plain old faithful SN2. But we have a little bit of a dressing we need to unravel before we get there. So, what I think is the trick here, I wanted to make it a little tricky, is if we step this back, I think it would, so this is I think a scenario where it really helps and pays off if you draw back to what you want to get to. I think it's very, very, very not too tricky to see that if I drew this, you can see the 1, 2, 3 carbons right there. You can see that at this point in time, like this is the product of an SN2 reaction where we had enolate attack this. That's what I'm trying to say. Of course, I'm jumbling my words. So, how do we get from here to here? Unfortunately, time to be annoying again, sorry, but you reach back in your head and get some old Ochem I knowledge. If we hydrate a triple bond, right, we know that we can end up with a carbonyl because of a keto-enol tautomerism. And we can get the least substituted or the more substituted product. In this case, it's the more substituted product. So if you just throw in some mercuric sulfate and H2SO4, that's how you will hydrate the triple bond. And you know what, I'm gonna take back, I'm not even sorry, because that is the beginning of Ochem II stuff because of keto-enol tautomerism. So, if we even go first, so that was, I think, a big trick. If we step this back once more, now we can actually get to the part where we can draw a cut, like right here. So my enolate is obviously the benzene ring and the 3 carbons right here. And that enolate looks like this. I don't have to draw the hydrogen. I'm not going to because it's a little weird, but you could draw it in right here if you wanted to. And actually, no, we'll leave it. It's not as weird as I thought. And down here, luckily, all we need is the starting material. So, 50% down, 50% more to go. So let's just keep going one step back at a time. I need to make this, well, I need to make the enolate, right? So how did I look beforehand? Well, I just had an aldehyde, right? I just had this sucker. So to make that happen, there's only one way I can make my enolate, right? There's only one alpha carbon to that aldehyde. So, I don't know, just use some LDA. Whatever you want to use. Your choice. So, what do we do next? So now we have this situation where we somehow got 3 carbons onto the benzene ring. And I'm going to make some space over here. It would be super nice to use some type of electrophilic aromatic substitution reaction. However, we're not as lucky to have a carbonyl on the benzylic position. So we might have to think about how we're going to properly do this. So what I think is a little bit easier is it would be really cool if we also just continued on this SN2 train and we had like this benzene ring. Like you see we have 3 carbons in a row, right? We're attached at one end and we have functionality towards the other end. So what if we had something like this? Sorry, that's not a bend, that's just bad handwriting. Like this, right? This looks more manageable because we could then take this back one step further and have a benzyl grignard and also attack this again, right? Because this would just be SN2, right? So this is all valid, but we need to figure out what reagents go here. Well, very similar to over here, we need to hydrate this triple bond. However, this time we need the least substituted position. And I never remember all these reagents, but I know you need BH3, or people like to write BR2, H, whatever. So BH3, H2O2, water, OH minus, the whole gambit, the whole gang's there. Everybody's helping out. But that's how we can hydrate the triple bond to get the aldehyde, the carbonyl, in the least substituted position. So this is starting material. And because we do our due diligence, and we need to get all the way back to benzene, whoa, all the way back to benzene. One step back with magnesium gives me this with a bromine. And now we reach for that electrophilic aromatic substitution knowledge. We use some BR2 and FeBr3 to make it happen. So I think you're still with me. You're still hanging up in the gallery. This is pretty comprehensive, and even though we may not have covered everything in alpha carbon chemistry wise, we did a whole lot. And not only in doing that, but we resurrected a whole bunch of knowledge you may not have used in a while. So it's a win as far as getting the juices churning, because maybe you were thinking, did I have to do a Michael here? You remembered where Michael was, right? A Michael addition. That's maybe not what we did in this problem, but you remembered consciously that a Michael addition is a 1,5 dicarbonyl relationship at the very end. That's kind of what I was talking about at the beginning of the video. Okay, gang, thank you for hanging with me. Thanks for chilling. Thanks for partying. Not really, but thanks. If you like the video, right, you know, obviously keep watching, and visit jochem.io. Give me a follow on Instagram, jochem_io. Like me on Facebook, just jOeCHEMio. Tell your friends, tell your family, tell your dogs. Everyone always forgets cats. Tell your cat. But thanks for watching, and I'll see you in the next video.